Hello everyone, this is the Space Channel. The topic of black holes constantly pops up in mass culture, and it is covered with a whole pile of various myths. Quite often, under our videos, subscribers ask questions based on those myths they once saw or heard. That is why we decided to create a series of videos debunking the most common myths about black holes. In the previous two parts, links to which you can find in the description, we have already examined 8 widespread myths about black holes, and today we will look at 5 more myths about black holes. Let's go. The myth under number 9 claims that Hawking radiation and jets burst out directly from the interior of a black hole. According to the theory of relativity, nothing can leave a black hole. Still, when it comes to Hawking radiation or to black hole jets, you can often hear phrases like Hawking radiation coming out of a black hole, or jets bursting from a black hole. Such expressions are not correct from the point of view of physics, but in the scientific community, where everyone is, so to speak, in the know. Simplifications in language are widespread. Therefore, among people far from professional astrophysics, the idea arose that matter is ejected from beneath the event horizon of a black hole. In addition, in images of a black hole, the jets really look as if they are bursting right from the middle of the black hole. Where, then, are all these particles actually flying from? Hawking radiation is formed above the event horizon, however very close to it, so it may seem that it flies from beneath the event horizon. We examined this process in detail in one of the previous parts, so we will not dwell on it further now, and will take a closer look at the jets. If we look at common images of black holes, we will see giant streams of matter burst from their poles. In fact, these are the jets, or, by another name, relativistic outflows. The mechanism of jet formation at the moment is poorly understood, but it is believed that they form as a result of a complex interaction between the accretion disk's matter, the magnetic fields it generates, and the black hole's magnetic field. As a result of this interaction, charged particles from the accretion disk can tap energy from the black hole and accelerate to speeds close to the speed of light. After that, they are ejected along the axis of rotation of the black hole. However, at the moment, there is still no final confirmation of this jet model. The 10th myth can be formulated as follows. The larger the black hole, the faster it evaporates. This myth comes from our everyday life. When dealing with liquids, we are used to the idea that the larger the surface area, the faster a liquid evaporates, and we transfer this experience to everything we call evaporation. But the evaporation of a black hole occurs according to a completely different principle. Hawking radiation occurs due to the separation of virtual particle pairs by tidal forces. The larger the black hole, the weaker its tidal forces are. Because of this, the larger the black hole, the smaller is the region around the event horizon in which the black hole can separate pairs of virtual particles. Therefore, each second it separates fewer particles and loses less mass. That is why the evaporation of large black holes proceeds extremely slowly. For example, a black hole with the mass of the Sun would not have enough time, even over the entire lifetime of the universe. For a black hole with a mass of 1 trillion kilograms, 10 to the 12th kilograms, which is 1 trillion times less than the mass of the Earth, it would take approximately 14 billion years to evaporate. In contrast, a hole with a mass of 1,000 tons should evaporate in only 84 seconds. According to the 11th myth, a micro-black hole could form in the Large Hadron Collider and destroy the world. This myth has existed for quite some time. It first appeared long before the Large Hadron Collider was conceived, and it regularly surfaces during the construction of every new particle accelerator, when journalists try to hype up public panic. This myth has a factual basis. The thing is that when subatomic particles collide at enormous speeds, micro-black holes can theoretically indeed arise. However, as I already said in the first part, black holes do not work like vacuum cleaners, so the appearance of a black hole in a collider carries no threat either to the Earth or even to the people who work at the collider. The fear of the formation of a black hole was actively sustained by the mass media and various representatives of pseudoscience right up to the launch of the Large Hadron Collider, as it had been before the launches of previous accelerators. Interest in this myth vanished abruptly immediately after the collider's launch, when it turned out that nothing was happening. The world was whole and unharmed. Moreover, not a single trace of micro-black holes was detected. In addition to the fact that such small black holes should evaporate extremely quickly due to Hawking radiation, they must disappear much faster than we can record them at the current level of technology. With all that, a collider is only a weak parody of the natural accelerators that exist in space. Thanks to them, the Earth's atmosphere is bombarded by particles with energies 1 billion times greater than those that can be obtained in a collider. The formation of micro-black holes in this case is significantly more probable, and it is quite possible that they do form there, and every month, several such black holes can sweep past each of us, absolutely unnoticed. The 12th myth can be summarized as follows. Black holes do not interact with massless particles and neutrinos. The roots of this myth lie in the school curriculum, in which the Newtonian law of universal gravitation is considered, and the general theory of relativity, if it is touched on at all, is covered superficially in a few words. According to Newton's law of universal gravitation, only objects that have mass attract each other. Therefore, people who are not familiar with the theory of relativity reason as follows. Photons have no mass. Thus, the force of gravitational attraction between a photon and a black hole equals 0, and therefore light should be indifferent to gravity. But all this is correct only within the limits of Newtonian gravitational theory, which, although revolutionary for its time, is now outdated and incorrect in many respects. Newton's theory of gravity was empirical. It provided a convenient formula for calculating the force of attraction between bodies, but it did not explain why it arises. The general theory of relativity explained gravitational attraction by the curvature of spacetime. The curvature of spacetime created by an object is called a gravitational well, and the more massive the object, the deeper its well. For massive objects, it is intense, and for a black hole, it is, in fact, infinitely deep. Photons move in straight lines in spacetime, but when this line passes through the gravitational well of a black hole or another massive object, it is curved along with the space. This effect has been known for a long time and is called gravitational lensing. Thanks to this, we see a bright glow around black holes. This is the light of many stars located behind the black hole. Moreover, we can see the light from one star on different sides of a black hole. Photons that have fallen into the event horizon of a black hole find themselves at the bottom of its gravitational well and must overcome an infinite distance to escape. That is precisely why a black hole does not let light escape. A photon's attempt to escape from a black hole is like a person trying to run to the end of a treadmill. The same situation applies to neutrinos. They interact very little with matter and have a tiny mass. Because of this, many people believe they should not interact with black holes and therefore will pass through them. But black holes do not allow neutrinos to escape, just as they do not allow photons to escape, due to the infinite curvature of space. The last myth for today, number 13, can be summarized as follows. Black holes are objects made of a special substance, and the event horizon is the material surface of these bodies, and you can chip off a little piece of it and keep it as a souvenir. I do not know exactly where this myth came from. Still, on our old Telegram channel, we very often received questions about what a black hole feels like to the touch, what it is made of, and how black holes can have different sizes if the event horizon is immaterial. What we see in images of black holes is not the holes themselves, but their shadows. When an object collapses into a black hole, it compresses into a singularity, which, in the simplest case, is a point and therefore has no size. Around the singularity, an area forms in which the curvature of spacetime is infinite. Nothing can leave this area, including light. The boundary of this area is called the event horizon of the black hole. This is an immaterial boundary in space from beneath which light does not escape. It is the diameter of the event horizon sphere that is usually taken as the size of the black hole. Because the event horizon does not let light escape, it is impossible, in the literal sense of the word, to capture it with a camera. Still, in its place in the image, we can see absolute darkness. So when people talk about an image of a black hole, they call it a shadow. And what about the matter beneath the event horizon? Well, when matter compresses into a black hole, its density and properties change. First, it becomes neutronized. That is, protons merge with electrons forming neutrons. Then the neutrons merge into a single hole, and the object begins to consist of bound quarks. There are even hypotheses about the existence of such quark stars that never became black holes. Based on this, it seems pretty logical to assume that this process should continue, and as a result, the black hole will simply consist of some special particles. And in fact, that is what happens, but not quite in the way people imagine it. As a result of the compression, a single particle effectively appears, called the singularity. The point is that particles are, in essence, clumps of energy, and as compression proceeds, the boundary between them disappears and the clumps merge. This continues until they form a single clump, compressed into a point. The separate particles disappear, forming a singularity in which the very notion of a particle loses its meaning. Therefore, it is not correct to say that a black hole consists of some particular substance. At the same time, I have considered the simplest form of a singularity, simply a point. Still, in a real black hole, it has an entirely different shape and rather specific properties. But we will tell you about that someday in a separate video. That's all for now. If you liked the video, give it a like and subscribe to the channel. See you next time.